Okay, today we're going to be learning about exponential functions and how they work in the real world. Exponential functions are probably our most important type of algebraic function that you will use. It's where money is used, it's where population and census are done. How do you predict growth and how do you predict decay? So this model is basically the most important model mathematically, I would say. It's a function that looks like y is equal a b to the x, where a cannot be 0 because 0 times anything is 0, and b must be greater than or greater than 0 but cannot be 1. This model is used mostly in real life, and it's for growth, decay, and money models. So we all love to see our money grow, so this is what it's going to look like. A growth model has the value of x increases as the value of y increases. So this would be an example of a growth model. That is what we want our money to do. Okay? A death or a decay rate is going to be when x increases, the value of y decreases. So basically what you're going to see is in our world, our men and women are living longer and they're growing older. Does that make sense? So our decay model is decreasing instead of increasing. We are living longer. That's what we call exponential decay. Okay? So an example, if I give you y is equal ab to the x, growth is going to be when your b value is greater than 1. Growth is going to be when your b value is greater than 1 and your a value is greater than 1. Decay is going to be whenever your a value is greater than 1, but b is a fraction between 0 and 1. That is going to be your decay model, okay? Now, we have what we call our growth factor and our decay factor. That is actually going to be our value that we're going to be looking for, and I'm going to talk about that here in a second. The biggest thing I need your brain to understand is your y-intercept is always 0a, and then you're going to have an asymptote at y equals 0. An asymptote is going to be the point on the graph where it approaches. It gets really close to it, but it never, ever crosses. For example, if we go back to this right here, you can see that this right here is going to be our asymptote. It is actually going to be our lovely x-axis. It gets super close to it, but it never crosses it, okay? Now, it says to identify each function or situation as an example of exponential growth or decay. Exponential growth or decay. And then also say what the y-intercept is. So we want to know growth or decay and the y-intercept. Those are your key goals here today. So our y-intercept is super easy. It's going to be this. So our y-intercept is the value 0, 12. Super simple. Then I want to know if we're going to have a growth or if we're going to have decay. So you're going to look at this value right here that has the exponent on it. Since that value is between 0 and 1, meaning 0.95, that is less than, this is going to be decay. And whenever I ask what my decay factor is, you're going to say that it's 0.95. Okay? Next one. So right here, I'm going to have my y-intercept. My y-intercept is going to be the ordered pair, 0, 0.25. And then I'm going to next look for growth or decay. Well, that is going to be my b value greater than 1 because 2 is greater than 1. So I'm going to have a growth, and my growth factor is going to be 2. Okay? Next one down here. It says you put $1,000 into a savings account for 4 years. The account pays 5% interest annually. Is this going to grow your money or is this going to decay your money? If it says that it's going to have interest, interest means that it's going to be bigger, and I'm going to have 100% plus 5%. So that means I'm going to have 105%, and if you put that into decimal, that's 1.05. This is what we call our growth. Okay? So I now know that I'm going to be growing, and then it says, well, what is my a value? Or I should say, what did I start off with? So that means my y-intercept is going to be what I started off with, which is going to be 0, 1,000, because that is how much I put into the account. Okay? So here's our model that we have, and this is your brain what you need to understand every time we're calculating this. 1 plus R is going to be your rate of growth or decay. Now, if you're adding to it, like we just talked about in our previous example, it's going to be growth. If you are subtracting from it, and let's say the population's decreasing by 10%, then it's going to be 1 minus that. So 1 represents 100% of our population. R would represent the 10%. So right here, I have A at T. A at T is going to be my number that I'm looking for overall, and then the initial amount is going to be what we start off with. So for growth or decay to be exponential, a quantity changes by a fixed percentage. So important, okay? So important that your brain understands that. Now, with that being said, let's go ahead and do our first example. You invested $1,000 in a savings account at the end of 6th grade. So I'm going to tell you straight up, your A is how much you started off with. That's the initial amount. The account pays 5% annual interest. So what this means is the account is going to get 100% plus another 5%. Be nice if I could erase the whole thing. So that means I have 105%. We're going to change that to a decimal. So that's going to be 1.05 is what we're actually growing. So how much money will be in the account after 6 years? So my equation is going to be A of T is going to be A times 1 plus your R to the X power. Well, A is the initial amount, which is the 1,000. And we already know that this whole thing is going to be your 1 plus your 5%. So this is 1.50 to the X power. That's my equation. Your X is going to be how many years you have this in your account. So this is going to be 6 years. So I'm going to have 1,000 times 1.05 to the 6th power. So if I come over here to Desmos and I type this in exactly the way I have it, 1,000 parenthesis 1.05 raised to the 6th power. That means I'm going to have $1,340.10. So that's how much money we will have in our account. This is the answer to our problem. Okay, next. Tonight's homework is actually going to be, I'm going to start it with you right now. It's going to be 7-1 worksheet 1. And number 1, it says, without graphing, determine whether the function represents exponential growth or decay. So, very first thing you're going to do is this is going to be growth or decay. 1/3, is that a fraction between 0 and 1, or is the number larger than 1? Since it is a fraction, I know immediately that I'm going to have decay, and my factor is 1/3. And then it says, what is my y-intercept? Well, my y-intercept is going to be this value right here, so that's going to be the point 0, 0.99. Okay? Next, number 2, it says, without graphing, determine whether the function represents exponential growth or decay. So let's go on the inside. That's 1.75. Is that larger than 1 or a fraction? It's larger than 1, so that means I'm going to have growth. And 1.75 is my growth. And then I want to know what my y-intercept is. My y-intercept is going to be this right here, so that's going to be 0, 20. So that is how you're going to do problems 1 through 4. Next, number 5. It says, suppose you deposited $1,500 in a savings account that pays interest at an annual rate of 6%. So we know that we have y is equal to a, 1 plus r to the x. My initial amount is going to be my a, which is $1,500. Then I'm going to have 100%, which is the 1, and then I'm going to have 6%, so that's going to be 0.06. I'm changing this from a percentage to a decimal, and that's what is going to go right there. So this is 1,500, and then 1.06 to the x power. No money is added or withdrawn from the account. So this is my equation that I'm utilizing. So now what I have to do, okay, so part A says, how much money will you have in your account after 5 years? So all you're going to do is you are going to plug in for x, you are going to put the number 5. So I'm going to come over to Desmos, And over here, I am going to plug in my equation, which is 1500, parenthesis, 1.06, close parenthesis, raised to the, how many years do we have that in there? 5 years, and that's going to be $2,007.34. So I'm going to come back over here, and I'm going to put that down. $2,007.34. Okay? Same thing, part C, I'm skipping over to part C. This is how many years will it take for the account to contain $2,500? So this is going to be a plug and chug. This is like a guess and check scenario. So I'm going to come back over to here, and I want to know when I'm going to get back up to there. So I'm just going to keep changing this amount. For this 5, let's go ahead and make this 8. Nope, need to go more, make it 10. Now I'm over the 2,500, so let's back it down to 9. Close, that's probably going to be my winner. So we have to be at least 2,500, so it's going to take 9 years. And that was with me just guessing and checking. So it's going to take 9 years for me to get the amount of $2,500. I have to have at least that amount, so it's going to be 9 years. Okay? Write an exponential function to model each situation. Find each amount after the specified time. A population of 1,236,000 grows 1.3% per year for 10 years. Okay, so our equation is going to be y is equal to a parenthesis 1 plus r raised to the x. Yes? My initial population is this right here. That's what a is going to be. So I have 1, 2, 3, 6, 0, 0, 0. Then it says it grows 1.3%. So what that means you're going to do is you are actually going to have what in there? You're going to move this over 2 units. It grows. So it's 1.3%. So this is going to be 0.013. So you're going to have 1 plus 0.013 to the x power. So my equation is 1, 2, 3, 6, 0, 0, 0, and then 1.013 to the x power. I want to know how much population I'm going to have after 10 years, so that's what x is going to become. So my answer is going to be y is equal to 1, 2, 3, 6, 1.1013, and then 10. So I'm going to come over, and I'm going to type that in. So 1, 2, 3, 6, 1, 2, 3 zeros, 1.013, and then I'm going to raise that to the power of 10. So my population, for whatever I'm measuring, is going to be 1,406,413. That's what you're going to be utilizing. Now, we don't know. We really don't need the decimal here, and the reason why we don't know the decimal is because we're talking population, right? We're not talking money. So since we're not talking money, I can't have a 0.17 of a person or an item or a thing. So you're going to leave off the decimal on that because you are not going to need it. Okay? All right. Next, number 7. A population of 752,000 decreases. Okay, so I go back over here. Here's our formula. My initial is here. So that's y is equal to 752,000. And then this decrease is 1.4%. So I'm going to change this right here, this decimal, moving that over 2 units. Yes, moving that over 2 units. To be 0.014 value is a number. And if it's decreasing, my brain needs to understand I'm subtracting, not adding. Yes? And then our brain also needs to understand that x represents our years of 18. So I'm going to have 18 here. Yes? So if it decreases, you are going to take 1 minus 0.014 to give you point, and I want to make sure that you guys all see this so that you see this appropriately, 1 minus 0.014 is going to be 0.986. Raised to the 18th power. And that is going to give us the value (752,000) parenthesis 1 minus, and you can go ahead and put it like this if you want so that you know you did not mess up any calculations. It does not matter. And we're going to have 18 here. So that is going to give us 583,448. 583,448. Yes? That is number 7. Okay? Number 9. If we look at number 9, it says for each annual rate of change, find the corresponding growth or decay rate. So if I'm at a 45% growth, that's a plus. I'm going to take 1 plus 0.04 plus 0.45, and that's going to give me 1.45. That is my growth. Okay? This right here says it's minus, so I'm going to change this percentage to a decimal. So this is going to give me 1 minus 0.10 to give me 0.90, and that is going to be my decay factor. That's how you're going to do problems 9 through 12. Then number 13, it says in 2009, there were 1,570 bears in a wildlife refuge. In 2010, the population had increased to approximately 1,884 bears. If this trend continues and the bear population is increasing exponentially, how many bears will there be in 2018? Okay, well here's what the biggest thing you need to find out. You know that your population is growing, and we need to find out how much it is growing. Yes? So what we're going to go with is we're going to find out what we had versus what we started with. So in 2009, there was 1570, and then in 2010, it increased to 1884. And that is a 1-year difference. So what we're going to do is we're going to just use our formula that we have the entire time. And we know that our initial amount was 1570, and we know that our ending amount, which is going to be y, is 1884. I don't know my rate, but I do know that it was going to be 1 year there. So this 1 right here is not even needed. So we're going to distribute this lovely little 1570. And then I'm going to subtract this 1570 over because we're trying to find our rate. Yes? We're trying to find our rate to give us 314 is equal to 1570R. Now our rate, we are going to take this and divide it to find R. And if you take 314 divided by 1570, your rate is going to be 0.2. That's the rate at which this thing is changing. Well, that's super important because in order for me to do predictions, y is equal to, I know my initial amount, which is 1570, and now I know that this is my rate at which it's increasing. So I'm going to have a 1 plus 0.2 raised to the x power. So this is my formula to do any future predictions for any year that I want. Well, this wants to know the year of 2018. So how many years is there difference between 2009, which is our initial, and then our end, which is the 2018? Well, there is 9 years difference between there, so we're going to have x being 9. So whenever we plug this in to Desmos, what you are going to have is 1570, parenthesis, 1.2, parenthesis, raised to the 9th power. And it's going to give you that you have 8,100 bears in 2018. So you are going to have 8,100 bears in 2018. And that was a little bit harder because we had to find the rate first. And all I did is I went ahead and I put the information that we knew that happened between 2009 to 2010, and that gave us our rate first. Okay, number 17. The price of a new home is $350,000, sorry. The value of the home appreciates. What's appreciate mean? Appreciate means that it is going up. It's increasing. And this is increasing the amount of 2% each year. So how much will the home be worth in 10 years? So we're going to go right back to what we know. I know the amount that I have the house currently is $350,000. And then I'm going to add 1 plus my appreciation rate, which is 2%, which is 0.02, and then raising that to x power. The x is going to change into the value of 10 because I want to know how much it's going to be in 10 years. And that is going to give me, if I come over to lovely little Desmos and type that in, 35000, parenthesis, 1.02, raised to the 10th power, and that's going to give you $426,648.05. That is how much money we are going to make on selling your house because it's appreciating that amount of value. And that is section 7.1. If you have any questions, please let me know.